have getting data, whether to diagnose whether a storm is severe, the NWS still needs ground truth verification, and that's where you, as a SKYWARN spotter, serve a critical role. Now, after we review storm types, we'll start talking about identifying radar signatures, such as mid-level rotation, the bounded weak echo region or BWER, low-level mesocyclone signatures, as well as downburst signatures. Now, in concert with these radar signatures, we'll provide examples of how they manifest themselves visually, and this is what you'll likely be looking at in the field. Now, we will talk a lot more about radar than we have historically in our advanced class, and while radar is a great tool, it's imperative that while out storm spotting, you as a spotter report what you see out your window and not what you see on the radar. Let's talk line. Main themes are usually handled. And the important themes is to note that storm organization increases generally with increasing atmospheric wind shear. And we'll talk a little bit more about wind shear in a few slides. Now, if you're a new SKYWARN spotter, you may be unfamiliar or struggle with the concept of wind shear. Wind shear is defined as a change in wind speed and/or wind direction with height. Now, wind shear can be calculated from weather balloon or radar data and can also be forecast by computer models. Let's look at the two main types of wind shear: speed shear and directional shear. Oftentimes, we have a combination of both speed and directional shear. On some days, we can directly observe wind shear, and the images on the right bear that out. We'll talk about how we examine wind shear data. Now, in this example, in the top right, note the length of the arrows, actually top left, note the length of the arrows increase from the bottom up. This represents near the surface, down here, and then as you go higher and higher, that represents regions higher in the atmosphere. So we've got stronger winds at the top portion of the atmosphere than compared to the lower portion. And if we take a look at the clouds here in the image on the right, we see that the top part is sheared off a little bit more to the left than the bottom. And these, what we call Kelvin-Helmholtz waves, indicate that we have a tremendous amount of speed shear in the atmosphere. Now, if we take a look at the time lapse here in the bottom right, we notice that the base of the clouds are moving in one direction, while the top of the clouds are moving in another direction. And this indicates directional shear. And so again, winds maybe in the lower portion of the atmosphere are moving one way, while winds in the upper portions of the atmosphere are moving another. It should be pointed out that these two examples are very dramatic manifestations of wind shear. The absence of observing this type of cloud structure or motion does not mean that atmospheric wind shear is not available or present. About multi-cell storms, as the name implies, is a storm with multiple updrafts. The main hazards with multi-cell storms are strong to possibly damaging winds, especially associated with the outflow boundary or gust front. There is a large hail risk thanks to multiple updrafts, along with a heavy rain and subsequent flash flood threat. tornadoes can occur, but are typically not a big hazard associated with multi-cell storms. Now, a squall line may develop as environmental wind shear increases. Squall lines can really be thought of as a collection of multi-cells over a larger area and persisting with time. Now, the main hazards associated with squall lines are damaging winds, hail, heavy rain, and an increased embedded tornado threat. Our schematic to the right shows just how squall lines can produce damaging winds. A corridor or jet of strong winds typically flows from the rear to the front of the storm complex. As these winds encounter the area of greatest precipitation, or the strongest portion of the storm, the winds can be forced downward toward the surface. At times, these strong winds at the surface can outpace precipitation and result in the development of a shelf cloud. The strongest winds, and sometimes these embedded tornadoes, are typically found along the leading edge of squall lines. Examining the leading edge of the squall line, there are times where a shelf or sometimes a roll cloud will develop. Now, this area may look similar to the leading edge of the forward flank downdraft that we see in supercells, and the process in which they are formed are nearly identical. So typically, strong winds aloft reach the surface and spread out, resulting in sporadic areas of enhanced winds. Now, air will also ascend atop the surging outflow and can produce ominous-looking shelf or roll clouds. It is for this reason that shelf or roll clouds indicate thunderstorm outflow. Now, the radar image here that you see animating in the bottom left comes to us from St. Louis, Missouri on April 26, 2016, where a squall line was sampled by the radar near Chesterfield. Now, some of you may identify this radar signature, but if you're not familiar with it, this is what we call a bow echo. Now, this radar signature, or bow echo, suggests a high potential for damaging winds. If we take a closer look in at the lower levels, we'll notice an interesting appendage in the radar reflectivity field. This is from the 0.5 degree elevation angle. It mimics a little bit of a hook echo, which may imply a risk for stronger winds or even a tornado threat. If we examine our base velocity imagery while noticing the location of the radar, here located at Chesterfield, we see an area of brighter, cooler colors or an indication of stronger winds flowing toward the radar. Now, this corridor of stronger winds extends up to the 0.9 and even the 1.3 degree elevation angles, indicating some vertical continuity. And when there is vertical continuity in a signature, this yields greater confidence in the potential that this signature is not a radar artifact. And in this instance, it implies the potential for an enhanced area of winds. Now let's take an even closer look at the radar signature. If we annotate the imagery, we highlight the area of enhanced strong winds moving toward the radar. Now, just north of this area of enhanced winds moving toward the radar, we note a region of airflow actually away from the radar, as indicated in the red or the warmer colors. Typically, these are outbound velocities. Now, at this interface where we've got the outbound and the inbound velocities, this would be the area with the enhanced risk for damaging winds and perhaps a tornado threat. Looking at a broader picture, we see that this healthy line of storms extends across several counties, suggesting a potential for widespread damaging winds. Again, the area of enhanced winds really sticks out between the cities of Washington and Warrenton, and it is here that we could be dealing with the possibility or potential for destructive winds in excess of 70 miles an hour. Let's take another snapshot a few minutes later. Now, as the storms move over the radar, we see that the reflectivity structure remains largely unchanged. However, the velocity data, when you compare it to the previous image, may suggest that the threat for damaging winds has decreased. However, this is one of those gotchas with radar. Recall from our review with radial velocity, it may get the appearance that it is decreasing as the velocity associated with a target becomes more parallel to the radar beam. When the storms approach this so-called zero isotops, the ability to sample the true radial velocity becomes degraded. In short, I want to stress that this line is actually not weakening as it's moving over the radar. This is simply an artifact. If we advance just a little bit later in time, we see that as the storm moves farther east into portions of Illinois, the winds appear stronger. In fact, they more than likely never really weakened. Again, this is one thing to consider when interrogating radial velocity. If the targets are along the radar beam or along radial, the ability to sample the radial velocity becomes degraded, especially when you have targets along the zero isotop. We see here in this image that as the line of storms moves farther to the east, it's no longer along radial, and so the true radial velocity is able to be sampled. We'll next turn our attention to exploring radar downburst signatures, but let's look at a visual cue of the potential for strong downbursts. The image here shows what we call a rainfoot, and this is the telltale sign visually of strong outflow at the surface. Now keep in mind that this is an aerial image, so the scope of the downburst may not be captured fully from a ground-based perspective. And essentially what's happening is the precipitation generates what we consider or what we call negative buoyancy. And as that precipitation falls through the air, it cools, and that cold air becomes denser than its surroundings. That denser air has a tendency to sink, and it sinks down, hits the ground, and because the ground is impermeable, the airflow rushes out in all different directions as indicated by the airflow arrows here in both of these images. On August 29th of 2020, several thunderstorms developed to the northwest of the DFW Metroplex. While the reflectivity cores are apparent, note the lines in the radar reflectivity that propagate away from the storm cores. These fine lines indicate outflow boundaries, which are a result of rain-cooled air surging out from beneath the storms. These boundaries act as areas that can instigate lift and thus the development of new thunderstorms. As the animation loops, we see new storm development occur where these boundaries collide between Springtown and Azle here in northeastern Parker County and adjacent portions of Tarrant County. On days where we are anticipating a risk for damaging downbursts, it is oftentimes the storms that develop along these colliding outflow boundaries that produce velocity signatures that indicate the potential for 60-mile-an-hour winds or greater. And because these storms are focused or forced on these outflow boundaries, these cores will have a tendency to develop very, very rapidly at the mid-levels. The appearance of these stronger cores aloft can serve as a precursor for potentially hazardous weather at the surface. So as seen in this cross-section of the storm northeast of Springtown, there is a core of higher reflectivity values as seen with the pink values in the left panel. To the right, we note that we have an area of higher inbound radial velocities with an area of outbound radial velocities, and they're slightly more convergent. This is occurring around 10,000 feet above the ground level in the middle of the storm. So hopefully it's no surprise that we called this a mid-altitude radial convergence or a mark signature. Now, given this environment, which we're going to discuss shortly, we may have a precursor of the potential for a strong to possibly damaging wind event. Now, other than radar and satellite, weather balloon data is another important tool that meteorologists use to diagnose the thermodynamic and kinematic structure of the atmosphere. Now, we won't go through a complete review of SKY log P diagram, and that's the diagram that you see to the right. But what's important is the upside or inverted V that you see with the dew point line here indicated in the green and the temperature line here indicated in the red. Now, this inverted V signature implies the presence of steep low-level lapse rates and the presence of dry air below cloud base. We see these environments often in the summer when it gets very hot in the afternoon. Now, during this particular weather balloon launch, the air temperature was around 106 degrees with a dew point temperature of 68 degrees. Now, this large difference between the temperature and the dew point temperature also implies that there is a decent amount of dry air present near the surface. Now, taking a look at the weather balloon data above the surface also indicates that we have dry air in place until close to the 700 millibar layer, where the temperature and the dew point line are closer to one another. This type of environment is favorable for downbursts. So what physically happens in a downburst environment? Now, in a downburst environment, rain and sometimes hail fall out of the thunderstorm into a dry air or dry pocket of air below the cloud base. As rain evaporates and or hail melts or sometimes sublimates, the air becomes cooler. Cooler air has a greater density than that of warmer air, and when you place colder air in the presence of warmer air, that colder air is going to have the tendency to sink. This cooler and denser air at times can accelerate very quickly toward the ground. And as we noted in our imagery showing the rain foot, the air hits the ground, and because the ground is impermeable, it spreads out very rapidly in all directions. In some environments where the air mass, the low-level air mass, is very dry, even showers can produce gusty winds of over 40 miles an hour.